Today, we're going to learn about voltage, current, and resistance in electric circuits, and we're going to do it with practical examples and by building electric circuits. What we have is a switch. We're going to talk a lot about switches in a second. So this is I can open the switch up and open up the circuit, or I can close it, of course. We have over here, we have a wire connected to, this is just a regular incandescent light bulb. And on the other side of that, we have a return line going here to the power supply. So for voltage, there are many different ways to supply voltage. You can have a battery, you can have a wall socket. We'll talk about the difference between AC and DC very shortly, all right? But in general, you can have a power supply, which supplies power like to your phone or to your car or whatever. The voltage from the wall, a battery. In this case, I have a machine that's generating voltage that is pushing electric current out. Now, there's a red wire and the black wire. Don't get too wrapped up in it. I'm going to talk about the different current conventions in just a second. But just know that electrons are flowing out of this black wire, and they're going over here. And I know you can't see it too far as I get off camera, but this black wire then continues into the frame of this other camera. The electrons are now flowing into the light bulb. When they hit the light bulb, there's a lot of resistance in that light bulb, and it causes it to get hot, and it glows. The electrons flow through the light bulb into this terminal here and back around. Let's turn the voltage up a little bit and start to see some actual current flow. So there, the light bulb is illuminated. Notice that in order for any electric circuit to function, first of all, we have to define the term circuit. An electric circuit is a closed loop that causes electricity or allows electricity to flow. There has to be a closed loop. In this case, the closed loop, the electrons come out of this black wire, off the camera, you can't see it anymore, then they come into the other camera frame, through the light bulb, into this wire, which is looped a little bit, then it goes through the switch here, and then back around, and now back into the frame of the power supply right here. You must have a closed circuit. That's why it's called a circuit. It's a loop, right? Now, if I interrupt the flow of electrons, if I just open this thing and I break the circuit, and now there is no way for the electrons, if they were to get here, there's no way for them to go back through this switch because it's now open. And that's called an open circuit. So we're going to talk about open circuits, and in just a minute I'll show you what a short circuit is. An open circuit is just a circuit that has been essentially opened up and disconnected. It prevents the circuit from being closed, so you can't have any current flow. Once we close the circuit again, then of course the light bulb is immediately illuminated again. Now, I want you to repeat 16 million times. Voltage is the push. On this display, I have the top row, which is the voltage. So there's 2.25 volts. Voltage is I'm going to talk about it a lot more detail as we go. Voltage is the push. It's kind of like the pressure, you can think of it, but it's always between 2 points. So the pressure or the voltage, you can never say that there's only voltage at a point or only voltage at a point over here. You have to say that there's voltage between two locations. It's almost like going up a mountain, right? You know how high you are on the mountain. If you were to jump off, you might splat into the ground, but the difference from the height of the mountain to the ground is the potential difference. The potential for you to splat into the ground is higher if the mountain is very high above the ground. There's always a reference point. The ground level is the reference point, or sea level is the reference point. In a circuit, the reference point for this voltage on this readout is between these two terminals. So it's telling me there's 2.25 volts, which is, we'll talk about units in a minute. Volts is the units of push in a circuit, right? But it's the units of push that exist between these two wires. It's always between 2 points. Voltage is always between 2 points. You cannot measure voltage at a single point. It's always between 2 points. All right. The display right under this is the current, the electric current resulting from that push. In this case, it's 0.366 amps. So the unit of voltage is volts, and the unit of amps, or the unit of current, is amps, or amperes, right? I'm going to talk about milliamps and microamps and all that in just a second, but this is in the unit of amps. Now, this display is also computing the amount of power that's being delivered from the power supply. We're going to talk about watts later. That's the unit of power. It's related to work and energy and things like that. We're going to save that for a little bit later for a different lesson. For now, focus on the top two numbers. Notice what happens. When I turn the voltage down to 0, there is no push electrical push between these two terminals anymore. That means that there's no current. So when I dial the voltage to 0, the current immediately dropped to 0 because there's no pushing anymore, and there's no illumination of this light bulb anymore. Because there's no electric current, there's no pushing of the current around the circuit. Now when I dial it up just a little bit, I get to a half a volt. Here, 0.51 volts. And the display is telling me that it's supplying 0.222 amps. And there is electric current running around this circuit now. In fact, even though the light bulb is not illuminated, it's just that I can't see it right now because there's friction in the electricity moving through the light bulb, but it's not hot enough to make any light. But notice if I open this circuit, right? Then the current goes down to 0. There's still a voltage across here. Notice the voltage is still half a volt, but there is no current. Why? Because the voltage is the push. This display is telling me how much it's trying to push, but because I've physically broken the circuit, there is no current anymore. So there can be push without flow, right? Pretend that this is a water hose or something, and there's water inside of it. If I cover my hand at the end so no water can come out, and I blow, I can supply pressure to the end, and the air, as you think about air, is trying to get out. But if I cup it, I can have pressure without anything happening if I prevent it from happening with an open circuit. If I close the circuit again, immediately the current jumps back up. It's just not enough for me to see any light. As I increase the voltage, notice the current has increased. Again, not quite enough for me to see any light. It's not quite hot enough yet, right? Notice the power is going up too. That's the third line, right? Because we'll learn later, the power in watts is just the voltage times the current. Straight multiplication. Voltage times current in amps and in volts. All right, let's go up to 0.84. Right, I'm not seeing much. I think I'm seeing a very, very small, a very, very small illumination down here. So small you may not be able to see it on the camera, but notice when I increase the voltage, the current also increased. When I increased the voltage to a volt, the current increased, and now I can see a little bit of light because now I have enough current for the friction, the resistance in that light bulb is causing essentially friction, heating up the filament, and then it makes light, right? So we're going to increase it, and notice I want you to focus on these numbers. As I increase the voltage, the current is going up. As I increase the voltage, the current is going up. As I increase the voltage, the current is going up, and all the while, the brightness of this bulb is also increasing because there's more current flow. So notice that voltage increases causes current to increase. Now in the beginning of the lesson, I said it didn't make any sense when someone tells you, hey, there was 5,000 volts flowing in that circuit. Okay, that doesn't make any sense. Because now you know voltage doesn't flow. Voltage is just the pressure, the electrical pressure trying to make a current flow. But the actual current is what the second number is, the amperage or the amps. That is a measure of how many electrons, we'll get into the details later, but it measures essentially how many charges per second are flowing around in this circuit, right? Now if I increase this thing higher, to 2 volts, notice it's awfully bright. If I increase it too much, the light bulb will just get so hot it'll burn out, right? So that can obviously happen. I want to do it one more time and sweep, and I want you to focus on these numbers as I smoothly go to 2 volts. I want you to notice how, as I slowly increase the voltage, the push is increasing, and that's causing the current to increase. And we'll talk about later, but it's also causing the power in watts, which we'll talk about later, to increase as well. Voltage is push. It causes current flow. Now, there is a law of electricity. We're going to study it in a later lesson. I don't want to do any calculations here. It's called Ohm's law. It is a very simple equation that relates current and voltage and resistance together. Because now you know the voltage is the push, the current is what is flowing, and anytime it's flowing, it has to be flowing through a resistance. You see, this wire is a very good conductor, but it still has resistance to current flow. I'm going to draw a picture and show you why in a minute, but ultimately it's because the electrons are going through the wire and they're bouncing into other electrons and other atoms, and it impedes their flow. But wire, electrical copper wire, is a very good conductor, low resistance. This light bulb has a higher resistance. It's not something we've measured yet, but we know it has some sort of resistance, and that's why it's heating up, because the resistance is so high. It's like an internal friction going on there. So voltage is the push, Current flow is the flow, but anytime current flows, it flows through a resistance, right? Every material that you're going to work with on a daily basis will always have some non-zero resistance. The only thing that doesn't is something called a superconductor, and I'll actually show you a demo of that another time. I already have the superconductor, I just need to film it. It's a special material that has a quantum effect that has zero resistance. But in everyday life, every material you ever deal with will always have resistance. So as we go up and down, we get more and less current, of course, the power delivered as well. Now what I want to do is do the same exact thing, but insert different resistances in this circuit to show you how introducing resistance in a circuit can choke off or limit the current flow. Before we introduce resistance, we need to get the hang of drawing some very simple circuit diagrams. So this is the absolute simplest circuit that anyone could ever draw. And so what we're going to do is draw a few variations of it. What we have is a voltage source. There's a positive and a negative side of that. The electrons come out of the negative side. I have a lot more to discuss about that in just a minute. We form a closed circuit through something called a light bulb. Now there's a couple of different schematic representations for a light bulb. A very common one is just a circle with an X, but you might also see a light bulb to be like a circle with like some kind of loop inside that represents like the filament. So you might see it like that in a drawing. Now in reality, the wire here is physically made of copper. It has resistance, but when we draw wires and circuits, we sort of pretend the resistance is so close to zero that it doesn't really matter, even though you know that there's a very small amount of resistance in actual copper wire. So what you have here is some voltage, and we've been increasing and decreasing the voltage over there, and the electrons are flowing down this way. I have a lot more to talk about electron flow in a little while, but electrons physically come out of that negative terminal through the light bulb and then back around. Now that's the simplest circuit we can draw. How do we learn more from it and change it? What we want to do next is we want to introduce what we call a resistance. So we have these different circuit elements here, and these are different resistors that I've already picked. I'm going to show you in a different lesson how you can decipher. There are these color bands on these resistors that tell you what the resistance is. But the unit of resistance is in ohms. So as we have learned before, we talked about voltage being the push, that's in volts, current being the current flow in amps, and resistance is a new unit we have to talk about called ohms. Of course, you can have kilo ohms and mega ohms and micro ohms and things like that, but the base unit is called the ohms. These little bands that are on these resistors actually can be decoded, and I'm going to show you in a separate lesson how you can read these bands and know what value it is. But for now, we're just going to measure the value. I have over here a voltmeter, and I'll show you in a separate lesson exactly how to do that as well. All I'm going to do is turn this voltmeter. Let me see if I can get it where you can see it. I'm going to turn this voltmeter to the ohm position. I'm going to put it right back down here so the camera can see it. And hopefully, I can move these wires out of the way. You will be able to read that. And right now it's measuring nothing. If I touch the two leads together, and it's not measuring any resistance, you can see on that display it has a very, very low, it's bouncing between 0 and very, very low. And then what I do is I have this thing connected to a breadboard. I'm going to talk about a breadboard in just a second, but for now, notice that I'm going to touch one side of the resistor. Whoops, kind of messed up my little meter over there. Sorry about that. I'm going to touch one side of this resistor, and then on the other side, I'm going to touch the other side of the resistor, and I'm going to see what it says. This is a 1.1, 1.2 ohm resistor. Now the actual value of this resistor is 1 ohm resistance. It's not exactly 1 ohm for a couple reasons. Because I'm touching it with this probe, and so I have a little bit of resistance in the contact point. And also, these resistors are not 100% accurate. There's a tolerance to all of them, so they're not exact values. The bands decode to tell me this is a 1 ohm resistance, but when I measure it, it's always going to be a little different than the theoretical value, but it's very, very close to 1 ohm. In fact, that's going down, down, down. You can see it going down. If I push a little bit harder on it, if I really give a good contact point, you can see it gets down very close to 1 ohm. So what I want to do is I want to introduce this 1 ohm resistance into the circuit. How will I do that? First of all, let me open up the circuit. So there's nothing going on there. Let me disconnect the light bulb from this one side. And what I'm going to do is connect this to this side right here. And I'm just going to essentially open up the circuit, but now I have to reclose the circuit again. And I'm going to show you how this little breadboard device works. We're going to use it a lot because it's very, very easy and helpful to build circuits rapidly. So you're not doing soldering or anything like this. So here we have, if I can get it to stay down here, that's pretty good. Something like this. The way this breadboard thing works here is the resistor is plugged into this line here. When you see this line of little holes, this line of holes are all physically connected together underneath. So there's a wire coming from this terminal up here, and there's a wire, you can see the gray one, going and plugged in here, and the resistor is plugged in the same row. So anytime you plug something in any one of these dots, they're all physically connected underneath. So what's really happening is the electricity is coming here, it's going through the light bulb to the white wire, and then it's going in here, and then it's connected underneath here going to this point. Then it travels through the resistance, and then through the gray wire into the red, and then through the switch, and then back there. So now what I'd like to do is go ahead and close the switch, and let's turn on, let's turn this on. But what we want to do first, actually, before I do that, let's take the resistor out, and I want to get the brightness of the light bulb set first so we can see it. So what we'll do is we'll just, instead of putting the resistor there, I'll just connect it with a wire. So now we essentially have the same exact circuit we had before, and I'm going to bring this thing up to about, let's just make it pretty bright, but not too bright. Let's make it right around 2.5 volts. That's pretty bright. All right, so we can see the light bulb, we can see the brightness. Now what I'm going to do is I'm going to remove this, and I'm going to open up the circuit so that I don't hurt myself. And I'm going to plug this thing in, and essentially I just replaced the wire with a 1 ohm resistance. So now I haven't changed the voltage, I haven't changed anything. The voltage is set the way it was, and now I'm going to close the circuit. So that's what we have right here. The brightness of this bulb is actually a little bit lower. So this is a 1 ohm resistance. This resistance right here is 2.2 ohms, and the one over here is, I think it's 4.7 ohms. So let's replace this one, right? And actually, let's do this first. Let's do this first. Let's take this out. Let's see if we can look at the current values. So when there was no resistance, right, we turn it on. We had 2.54 volts, we had 0.361 amps. So let's go ahead and write this down. It's 2.54 volts, and the current with no resistance was 0.360 amps, no resistance. Or no resistor in the circuit, all right? So what I'm gonna do is I'm gonna open this guy up, I'm gonna take this guy out, I'm gonna take this resistor, I'm gonna put it in place, and now I'm going to close it back up, and I can't really see too well, but I think it's a little bit dimmer. But here what I have is a new current. Notice the voltage is exactly the same, but there is less current, 0.344 amps. So same voltage, but with a 1 ohm resistance, it yields 0.344 amps. Now, same exact voltage, 2.54 volts, leads to a lower current. Why is that? Because there's now a resistance in series. All of the electrons flow through the light bulb, but they also flow through the resistor. And that essentially chokes down the current to a lower value. And so the light bulb, even though it's pretty close, it's a little bit dimmer, and the current meter tells us that there's less current flowing. Resistance impedes the current flow. It doesn't slow it down, it just reduces the value of the current flow. So let's speed this up just a little bit. I'm going to take this guy out, and I'm going to put a new resistor in its place, right? And we're going to measure the current flow there. So I'm going to put this resistor in place. Now this resistor is actually 2.2 ohms. So let's see what happens here. This is noticeably dimmer. I can definitely tell with my eyes it's a little dimmer. So the new resistor value we have is 2.2 ohms, and the current flowing right now is 0.319 amps. But notice the voltage is the same, 2.54 volts. 4 volts. But with a higher resistance, I'm getting a lower value of the current. When I increase the resistance in the circuit, it's lowering the current. As I increase the resistance, the current goes down because there's more collisions happening and essentially choking off the current flow. All right, so let's open that guy up. And then we're going to put our last one in. The last one in here is 4.7 ohms, so it's double the value of the resistance of the previous guy, and we should have about half the brightness. So we open it up, or we close it up, and we can see the light bulb now is very, very dim. And what is the current that we have in this situation? Right? Here we have 0.272 amps. And this was a 4.7, let me double check, 4.7 ohm resistance, but notice the voltage is exactly the same, 2.54 volts. So 2.54 volts, same voltage every single time, but as I increase the value of the resistance, the current is going down. And because the current's going down, the brightness of the bulb is going down. Now I want to do it one more time, but I want to do it in a slightly different way. What I'm going to do now is I'm going to put, this is the, I believe the first one that we had. And what I'm going to do is I'm going to do them all in rapid succession. So there's the 1 ohm resistor, and then here is the 2.2 ohm resistor, and then here we have the 4.7 ohm resistor. So now I have these two little jumper wires, and if I close it, nothing's going to happen. Why? Because the current is going into here, but there's nothing here. You have to have something connecting to the other side. So what I'm going to do is I'm actually going to connect this to this side of the resistor, and then this side I'm going to connect to this side of the resistor. So there, if I connect it without any resistance at all, it looks like this. If I put a 1 ohm resistance in, it looks like this, right? And then if I connect the other resistor, which is almost double that, 2.2 ohms, then it looks like this. And if I put the 4.7 ohm resistor in, then it's going to look like this. And it's very, very dim. So I just wanted to do it all in rapid succession like that, because when you see one after the other, you can really see how increasing the resistance lowers the current, and so the light bulb is much dimmer. So I want to draw these because I want you to get in the habit of understanding how to draw a circuit. So it's just going to take a second. This is the symbol for a voltage source, but now we have this resistor in series, we call it, with the light bulb. Series means that there's only one path for the current, and they're both in a straight line, so the current has to go through both of them, right? So you have some voltage here, you have the light bulb here, and in the first example, we had a 1 ohm resistance. So this is how you would draw that circuit, right? And in the second circuit, you would have, again, the voltage source, you would have a value of a resistance, you would have some light bulb, but this resistance in the second one was 2.2 ohms, so pretty close to double the first one, and we saw the current go down there. And then we have a voltage source, and we have the light bulb here. And then we had the last one here, this is a voltage source, we had 4.7 ohms. And so we have the current, again, circulating in all three of these cases, just going through a different resistor. Now you might say, well, wait a minute, we went from 1 ohm to 2 ohm, but the current did not get cut in half. We went from 2 ohms to about 4.7 ohms, that's about double the resistance, but the current didn't quite get cut in half. Why? Well, it's because when you draw the diagram out, you see that the resistance here that we put in there is not the only thing in the circuit. There's another thing in here called the light bulb. The light bulb itself has resistance. And so this is 2.2 ohms, and so we did double this resistance, but there's this huge resistance here also. When we use Ohm's law to calculate the current, we have to consider all of the resistance in the circuit. And just for giggles, let's use our meter here to measure the resistance of this light bulb. So what I'm going to do is disconnect this so that we don't have anything going on from anything else, and we will just measure across these two terminals what the value of the resistance of this light bulb is. So the resistance of the light bulb is 0.8 ohms by itself. So when in our first circuit here, we inserted a 1 ohm resistance. This thing almost has 1 ohm in each of these positions. So when we calculate the current using Ohm's law later, you have to use the resistance of everything in the loop. And that's why when we double the resistance, we didn't quite have the current. But we will do those calculations later to show you that Ohm's law, which we will learn in a later lesson, to calculate everything works for any branch of any part of a circuit. All right, now in the earlier part of the lesson, I taught you what an open circuit was. It's just whenever you open up part of the circuit, no current flows, and we can see there's no current flowing over there. I'm going to show you now what a short circuit is. We know that short circuits are bad. We're going to talk about why they're bad. We're actually going to burn out this light bulb in the process. So let's do it. Let's go ahead and close the circuit. We can see the light bulb here, but in this case, what I've done is now the circuit is going through this resistance as we have done before. We're still lighting it up. All right, what is going to happen if I have a stray piece of wire, just some kind of like, I don't know, some aluminum foil blows into your circuit, or something happens in your circuit where parts of your circuit are connected across each other. So for instance, you might have this wire here that came loose somehow, and it's just banging. Maybe you're in a rocket or something is banging, and eventually it comes and it touches the other side of this resistor. What's going to happen? Then the electricity is going to want to flow through the wire instead of the resistance, because electricity always wants to go through the path of least resistance. So as we short circuit it here, the brightness of this bulb, look at it, is going to get brighter. And look at the current over here. As it's at 3.343 amps. As I do the short circuit, the current goes up to 0.361. That is because, you see, the electricity is coming out of the light bulb and going in here, and then it has a choice when it gets to this point. It can go through the resistance, right? Or it can go through zero resistance. Now, I told you the wire is not really zero resistance, but it's very low. So when the electrons get to the junction right here, they're going to always choose, they don't have a brain, but they always go to the path of least resistance, or predominantly the path of least resistance, which is circumventing or short-circuiting the resistor. And because of that, there's no resistance in the way anymore, and so the brightness of this bulb goes out. Now let me show you why this is dangerous. So here, I've already got the circuit stable, and I know how much current this bulb can sustain. But let's increase the voltage here just a little bit with the resistance in place. Let me go up just a little bit more. Now we're going to short circuit it, and we burned out the light bulb. So what happened in that case is I designed the circuit, so to speak, to operate at a certain amount of current, right, that this light bulb is designed to take. But when a short circuit happens elsewhere in the circuit, the current surges because you're bypassing all the resistance in the circuit. You put the resistor in place in order to make the current to the right level for this light bulb. When you circumvent it, the current spikes and it burns out the light bulb. Now in a house or a car, a surge of current can cause a fire. So that's why you have the circuit breakers on the outside of your home, or if it's in a car, you have fuses that are designed to burn out if there's ever a short circuit. So short circuits are dangerous because the current surges and can actually cause a fire. And since we're getting the hang of drawing these things, let's go ahead and draw a quick little open circuit in a short circuit situation. So if you have some voltage source like we did, and it's going through some light bulb like we did, right? And through some resistance like we did, if it was a closed circuit, it would look like this. Some kind of open circuit you would draw. Well, you never really designed for open circuits, but a switch is just essentially an open circuit. So you would insert a switch there, which can then go to closed or open. And this is basically an open circuit at this location. Now, what would it look like if you had a short circuit? Now, you never draw short circuits in your diagrams, but I'm just telling you what's basically happening is that you have current flow going on in the circuit, and then some stray piece of wire accidentally comes off of this and just kind of flutters in the wind and accidentally touches down here. This happens very often, or can happen in airplanes and rockets with lots of vibration. Then what happens is when the current gets here, instead of going through going through this over here, then it basically goes through the short circuit and a lot of current starts to flow, which can burn up your power supply. Now, in our case, our short circuit wasn't connected like that. It was connected around the resistor. So the current got here and it just bypassed the resistor. That causes an increase of current, which burned out our light bulb. Now, to demonstrate voltage, current, resistance one more time and how they're related, there's an equation called Ohm's law. We'll use it later to calculate things. But now, let's try to understand them with an analogy. Pressure of your breath. Here is what I'm calling a straw, a really fat straw with a wide diameter. Here is a narrow straw with a very skinny diameter. Which one of these is going to be easier to blow through? Right? If I put my mouth here and blow, there's almost no resistance here. I can blow all day long, no problem. This, it's actually kind of difficult to blow rapidly through this. And if I made a very narrow straw, it would be very hard to blow. This has a low resistance, this has a high resistance. So for the same pressure, the same voltage in a circuit, if the resistance is low like this one, I can blow more current. same voltage, I can get more current to flow through this than I can through this. So we're going to learn later, and you'll learn it in physics also, that the resistance of a wire is related to its diameter. As you make a very thin, narrow wire, it has a higher resistance. Also, certain materials have higher resistance. Plastic doesn't have a lot of free electrons in the structure to flow, so high resistance. But metals like copper and gold and things, and other conducting materials have a lot of free electrons around the atoms, and so electrically they're very, very conductive. So we've done light bulbs. That's great. Let's do something a little bit different so we can get a little, just some variety in life. This is a little motor I actually took out of child's toy. It's something you can find almost anywhere. We'll take this light bulb out of the equation over here, put that aside. We're not going to need that. We'll leave the switch in place for now. And what we'll do is we'll connect the circuit around this motor here. So I have right here the switch in place with the motor. So again, as I increase the voltage, maybe 0.84 volts, nothing's happening because I have an open circuit here. If I close this guy, I can see the motor begin to spin. So in fact, I'm going to place this little whirly thing on top of there. All right, let's go ahead and increase it. When we increase the voltage, we start spinning very slowly. And as we increase the voltage, the current goes up through the motor assembly here. And so it's spinning faster, and hopefully you can hear it, faster and faster and faster and faster as I increase the current going through this motor here, okay? Now, I want to talk to you about the direction here. Not all motors behave the same way. It depends on how they're built, but this one can be rotated in two different directions. When I rotate it, it's going in this direction like this. And so it's blowing air essentially up, which is pushing the motor into the table. So I can send this thing pretty fast. And essentially it's blowing air up, so it's pushing the motor down into the table, so it's fairly stable. Let's go ahead and let it stop. Take this thing off, and the current here is flowing in one direction through the motor. Now what happens if we turn this thing around and essentially send the electric current in the other direction? If we send the electric current in the other direction, then the motor will turn in the other direction. It has to do with the forces. There's a magnet in here and a coil of wire, and when you reverse the direction of the current, the magnetic force is flipped around, and so the motor should turn. Instead of like this, it should go the other way, which means it's going to tend to lift off. So let's go and see, like here, let's see which way it is going the opposite direction. Again, as we slowly increase the current, hopefully it'll lift off. When I get to a certain voltage, it'll lift off and actually start to kind of fly. Let's see what happens. And there it goes. That's pretty neat. Let's do it one more time. I know there's no way I'm going to do this, but let's try to hit the camera, see if we can hit the camera. So we're going to go this direction. We're going to increase it. See if I can hold it still. Oh, not quite. Let's see if we can get it going a little faster before it goes off the rails there. Almost. Pretty fun. So as you reverse the direction through a motor, the motor spins the other direction, and I just wanted to show you that's a physical way for you to tell that the current flow is backwards or different when we reverse the wires in the connection on the motor. All right, the next thing I'd like to do is let's go ahead and take this kind of switch out of the equation here. We don't really need that anymore. We've talked about switches. And what I'd like to do is show you something neat called a light emitting diode. I know you've seen these things before. This is a blue one. We're going to talk about diodes a lot more in the future, but basically what this thing is, a diode is a one-way valve, so to speak, for current. It only lets the current flow one direction, right? If you flip it around the wrong way, the current can't flow. So it's very useful in circuits for lots of situations. But this is called a light emitting diode. That means it'll light up when the current is flowing through it. We can actually do some neat things with this. First, let's put it in the wrong direction, or well, let's put it in the right direction actually. And one of these leads actually is a little longer than the other. That's how I can tell which is which. When I connect it over here, and I have the voltage down to nothing, so I can then connect the current like this. Then I can increase the voltage. Now, different diodes activate at different voltages. This one, right around 3 volts is when it's going to illuminate. Whenever I decrease it, notice that it just kind of shuts off. It does dim a little bit. There is a range where it will begin to light up, but mostly diodes are an on-off situation. There's about a volt or about 3/4 of a volt in a range where it will begin to turn on. But once it's on, it doesn't really get any brighter, and once it's off, it's just off. There's a narrow range when it turns on. It's sort of an on-off kind of deal. So we get up, really it does nothing at all until we get up around 2.5 volts. Then it starts to come on, then basically it's fully saturated. So notice that this thing turns on. Let me get up to 2 volts. or 2.5 volts, 2.6 volts, right? If I take this thing out and all I'm doing is I'm rotating it around and putting it back in place, I'm going to turn the voltage back up to the same place, 2.5 volts. Let's get it up to 2, there's 2.6. And you can see that there's nothing going on because diodes only allow, they only conduct when the polarity is in the correct direction. It's like a one-way valve for electricity. Now, if I increase the voltage too much, I will burn up this diode. It can't resist electrical voltage forever. It can't resist that forever, but within a range, that's the job that it does. Now, let me flip it around one more time. And let's verify I didn't burn it out. Let's just turn it on and make sure it still works. It still works there. Now what we're going to do is instead of driving it with just a constant voltage, I just thought it would be neat to play around, since this is our first lesson in practical circuits, with to play around with some of the other equipment that I have here. We're going to use this equipment a lot later, so don't stress out about it. It's just fun stuff that we're going to use. This lower one here is called a function generator. It allows me to drive a sine wave or a square wave or whatever into anything I want. And so what I'm going to do is, instead of driving it with that power supply, which is a fixed voltage, what I'm going to do is drive it with this with a square wave, up, basically on, off. It turns it on and off, okay? And because I'd like to look at it at the same time that we are measuring it, I have this top piece of equipment called an oscilloscope, and that allows us to actually watch what's happening in real time. So what I'd like to do is connect, again, I've got the supply going across the diode here, and all I'm going to do is connect over here. This is just for measurement purposes, what's going on across that diode. So hopefully you should be able to see all of that here. And then what I will do, did I mess it up? Let's see here. Yeah, I think it's okay. And I'll press the output button here and see what happens here. We turn the output on and we see that this thing is now blinking, right? And we look on the top display and this oscilloscope is showing the voltage across this diode in real time. So this right here is the 0.0 volts. The top little hats up here are, I think I set it to 2 or 3 volts. Actually, I can read down here. It says 3 volts. So I'm driving at 3 volts, and then 0, and then up and then down, and then up and then down there. So it's turning on, off, on, off. Now, there's a couple things you can do with this. You can change the frequency. So right now it's at 1 hertz. That means 1 complete pulse up and down every single second. So let's change it. Instead of 1 hertz, let's change it to 2 hertz. And when I hit this button here, it's going to start blinking faster. And you can see it's blinking faster now. So 2 hertz, that's 2 cycles every single second. Let's change it to 5 hertz every single second. And you can see it's blinking much, much, much faster. Now, if you get crazy and start doing things like 10 hertz, then it's so fast that you can't really see it much anymore. You can barely see it here. And notice that our pulses got very, very, very narrow. And you would have to like turn the knob here to be able to spread them out to see them anymore. If you drive this thing with like, I don't know, 100 hertz, it's going to be so fast that we're not going to be able to really even see. The diode just looks like it's always on, right? So let's go back down to 1 hertz. And this was a square wave, which means it's just up and then it's just down to off. Let's change it to a sine wave, which is more gradual up and down. So instead of something like on and off, just flat top, we'll go to a sine wave. So we'll go to waveforms, and then we'll go to sine wave. Now notice how it's going to change when I do that. Notice how it's still going on and off, but it's more fading in and out, fading in and out, fading in and out, because the voltage is going up gradually and then down to a low of 0, and then up gradually and down to a low of 0 gradually like that. So sine wave, more gradual. You can see the thing turn on a little bit easier. And then square pulse, of course, is just more of a flat on-off type of situation. All right, now we go into the second part of the lesson where we dive a little bit deeper. We've done the practical. Let's talk a little bit about the theory. I keep talking about voltage as a push. Voltage ultimately comes from something called the electric field that you learn about in physics. Now, this voltage can be generated, or this electric field can be generated several different ways, but when we talk about voltage generation in real life, then there's really only a few different ways that we can get it, or that we can generate it practically speaking, right? We could do it with a chemical reaction. That's what's inside of a battery. There's a chemical reaction that tends to push electrons through to because of the reaction happening out one side of the battery and to try to accept them in the other side of the battery. There's a constant pressure between the two ends of the battery doing that. You can also generate it with solar cells. Photons come in, hit the solar panels, and it generates free electrons which flow out there. And the other way is in a power plant. In a power plant, what we're doing is usually we're taking a generator, which is a wire and a magnetic field, and we're turning the coil of wire inside of a magnetic field. And we learn in physics that that can generate a voltage and a flow of electricity also. If it's a nuclear power plant, you're just using the nuclear fuel to heat some steam up and turn a generator. If it's a coal-fired power plant, you're just burning it to turn a generator, to make steam and turn a generator. So most of our power generation involves rotating a wire in a magnetic field, unless it's solar or some kind of chemical battery storage. But when I say voltage is a push, I want you to have the following picture in your mind. Let's say that you have a mountain, and there's this mountain here. Now, you originally start at the bottom of the mountain. So here you are, and you got your little climbing boots on, and you're right here at the bottom. You're at the very lowest point. You don't have any potential energy at the bottom of the mountain, from physics. But as you climb and climb and climb, and eventually you become to the top of this mountain, you have gained a lot of potential energy, because now you're very high above the ground, and if you fall and hit the ground, you're going to hurt yourself. And when you're at the top of this incline, you have a rock and you throw it, and the rock then has a lot of potential energy, and it gets converted and gets faster to kinetic energy, and it hits the ground. Now the rock is at the bottom. Then you have a friend of yours, or maybe you parachute down to go over here and then get this thing, this rock, and you walk it back, essentially back to where you started, and you climb back up the mountain and throw it down again, and up and then down again, and up and down again. That is essentially what's going on, like in a battery or in this power source. What's going on is there's a potential difference between the two terminals of the battery, just like there's more potential energy at the top of the mountain than the bottom. But once it gets to the bottom, then you have to do some kind of work to bring it all the way back up the mountain again. You get tired bringing it to the top of the mountain. You have to burn calories from your food to do this. It takes energy to do this, but then when you get to the top, then you go to the bottom again. But eventually, if you keep climbing over and over and over again, your internal battery will go dead, because you will run out of the energy from your food, and you won't be able to carry the rock anymore. So your battery inside of yourself will wind down and die, right? Hopefully not really dead, but you know what I mean. You get tired. So in a battery, the same thing is happening. There's a chemical reaction that's pushing the electrons out of one terminal, and then when they go all the way through the circuit, they're kind of flowing downhill, going back down to low energy again. And then they go to the other terminal of the battery. But inside, there's a chemical reaction which takes that electron, which just came back to it, and through chemistry, through the chemical reaction, pumps it back up to the top. And then it goes through the circuit again, and then the chemical reaction pumps it up to the top, and then goes through the circuit again, and so on. But eventually, the chemicals in that battery will run out. They won't be able to take the electron and shoot it out the other side anymore, because the materials have all reacted inside. And so the battery's dead, and you can't do it forever, right? When we generate electricity with a nuclear power plant, we have a fuel, and it makes steam, and it turns a generator, and that generates electric current for the houses and all these other things. But when we run out of fuel, we run out of the electricity. We burn the coal. We burn the coal to make steam to turn a generator, same as everything else. But when we run out of coal, then we don't have any more electricity. So all we're doing is taking one kind of energy, either in coal or nuclear fuel, and turning it into another kind of energy, the potential energy of electrons moving in a circuit. But we don't get something for nothing. We have to get it from somewhere. And in terms of solar power, it comes from the sun. It's quote unquote free, but not really free, because we have to build the solar panels, and also the sun is doing its own thing. And it's been around for billions of years, so it's not really, it's free for us, but it's not like free energy, because it's generating energy from its own nuclear reactions, which will eventually burn out also. All right, but that's what I mean by the push. It's the push, and it pushes it always, notice, in a circuit. You have to have a circuit in order to keep this process going. If you open the circuit up, the process stops, right? Now let's talk about, after we get to the push, we have this current flow happening. You can think of this as almost like the current flow. So what would the current flow inside of a circuit look like? Right? We have a lot of different ways in which we can talk about that. Let me go and draw a basic circuit with some kind of voltage. And I'm not even going to draw any resistance inside of this circuit. I'm just going to put a closed loop. So there's some kind of circuit current flowing here. There's a positive and a negative terminal here in this battery. And what we say is the electrons come out of the negative terminal. So I'll say electron flow. right? Now, electrons are actually really what is flowing in the circuit. In our power supply here, it was the black wire. The electrons were coming out of the black wire and going through the circuit and going back in through the other side. However, there are alternative ways to think about it. When we get into circuits in depth, we actually think of it in a slightly different way. Let's think about this wire as a hollow tube. You can think about that tube that I had a second ago. And this is a giant cross-section of a piece of wire, right? And inside are copper atoms or whatever atoms there are. And every atom has some nucleus with a positive charge and some electrons with a negative charge, which are orbiting around. Now, in reality, copper has a lot of protons in the nucleus and a lot of electrons in the surrounding electron cloud, but I'm only drawing one of them for clarity. But just know there's lots of electrons in the outer shell and of the atom, and then there's lots and lots of protons in here. But it doesn't matter for this discussion. I'm just going to draw it like this, right? Now the next copper atom over has its own nucleus with its own electrons, and the next one over here has more, and the next one over here has more like this as well. So these are all electrons. So I'll just kind of draw like one more. I guess I'll continue off like this. Okay. When I hook up a battery to one side to the other, the chemical reaction is pushing with a pressure. It's really generating an electric field, if you want to get into physics, which is what pushes the electrons, okay? Now, what happens is this electron is going to then hop over to the next atom over. But as soon as it gets there, because electrons repel each other, what's going to happen is this one is going to want to jump to over here. But then these two are now crowded together. It's going to push the other one in a chain reaction over here. And this happens incredibly quickly, right? So it's almost like they're all moving at the same exact time. So you have one bumping into the next one, into the next one, into the next one. And I've drawn it like happening one after the other, but it's almost at the speed of light that they all move in lockstep. I want to show you something. Let's pretend that this magnet is an electron, and here's another electron, here's another electron, here's another electron, and there's our final electron. Instead of this moving, which then moves this one, which then moves this one, I want you to instead imagine them almost happening. I guess I'll move this one out of the way. Almost at the same time. They all kind of move like this, like together, but not really together. I mean, there is a delay, and so it's not all really together, but it's almost at the speed of light that they move with each other, right? I want you to imagine throughout the entire circuit, these electrons are kind of move in unison, almost. And so all around the wire, there's trillions of electrons. And when you apply a voltage, they all kind of hop to the next atom over, and then again, and then again, and they race around the circuit. Eventually, another electron will come around the other side and enter into the other end of the battery or into the power supply. One thing I want to tell you, though, is if you notice here, that right at this point here, once this one moves over here, right here, this is an electron vacancy. You might say that since there's an electron missing, we can make up another word for this. We can call it a hole. Why do we call it a hole? Well, because once the electron's gone, there's like a missing electron there, almost like a hole that you've dug there. But electric force is very, very, very strong. Actually, the electric force is millions and millions of times stronger than gravity. As soon as there's a hole in place, that atom is going to attract another electron and fill it almost immediately. So, you know, there is a time delay, but it will happen almost immediately because the electric force is so strong. But this thing leaves a hole so in its place. So instead of thinking about the positive electrons moving this way, you can think almost the negative electrons moving this way. You can instead thinking of imaginary positive holes moving the other way. Because if you think about that, those blinky lights, like in the marquee, like if you stare at it enough, you know what's happening is it's just like a blinking pattern, but you can almost see like the absence of a light going in the other way. If you watch those patterns of lights moving in a circle, sometimes if you stare at it, you can see like an absence of a turned off light bulb appears to move in the opposite way. So as you have these charges moving like this, since they're leaving vacancies, it almost looks like a positive charge because this, once you vacate, this whole atom will look positive. It will look like positive charges moving the other way. So the punchline is we know that really electrons flow out of the negative terminal like this, but it's the same thing as saying positive current flow flows this direction. So this is called the hole current, right? When you're studying engineering and when you're doing, when you get into circuit design, the current that we refer to is always the positive current flow. And it's just a convenience thing more than anything. When I look at this power supply, I can say that there's negative electrons coming out of here, or I can say there's positive fictitious charges coming out of the red one, because they're going to be the same thing. Negative electrons flowing one way is the same as positive charges flowing the other way. Mathematically, they're equivalent. And we love to have positives in our equations instead of negative signs. Also, when we get into magnetic fields, the magnetic field is the right-hand rule of the magnetic field is based on positive charges also. So it's easier to talk about positive charge flow almost all the time in electric circuits. All right, so that is the current flow. Now, what is resistance then? What is resistance? Well, it's just what you would think of. It's resistance to motion. You see, I drew all of these atoms lined up in a perfect little alignment here. But in reality, it's not like that at all. Right? Actually, inside of here, there's an atom with its electron right there, and then there's another atom, and then this electron is like there, another atom, electron like there, another atom with the electron, you know, right here. And by the way, I keep drawing these atoms like they have electrons that are little balls. Okay, electrons are not little balls like that. I don't want to get into quantum theory here, but electrons are waves, protons are waves, quarks are waves. It's all a wave theory. But I'm drawing it on the board like this for us to visualize it, all right? Just know that it's not a little actual ball orbiting, but it does help us visualize. But what's really happening here is this atom, because it's at a certain room temperature, it's agitated. Everything's vibrating, even at room temperature. So this atom is moving this way, and this one is moving this way, and this one's moving this way, and this is moving this way. And the electrons are jiggling too. So whenever this electron tries to hop to the next atom, it's going to scatter off of one of these atoms and maybe ricochet. And then it's going to hit another atom at an angle and maybe ricochet. And then it's going to hit another atom and maybe ricochet. So it's not really a nice even hop that's like no resistance, just going sailing right through. In reality, every electron, when it's jumping to the next atom, is usually being scattered off of another electron or off of a nucleus or some impurity in the copper or something. And it's basically getting impeded, and then it changes direction and it changes direction. That is what leads to resistance. Now in copper, there's not as much resistance because of the way the electrons are arranged around copper atoms. But in a plastic or in a rubber, there aren't very many free electrons, so it can't jump so easily, and the resistance is much, much higher. That is the physical meaning of resistance. So we say that voltage is the push. The chemical reaction or the reactor is the push. It tries to push electrons, which is the current flow, but the electrons are moving through a medium which impedes its flow, and we call that resistance. All three of these things are related by something called Ohm's law, which we'll study very soon, and allows us to calculate the current or the voltage anywhere you want in a circuit. So I hope that clarifies how voltage, current, and resistance fit together. Now I'll say one last thing, and that is that everything that you'll ever use in a circuit has resistance of some kind, even wires. However, as you cool things down, usually the resistance goes down because the thermal motion, the agitation of everything in the circuit, like even the atom, slows down. There are special conductors called superconductors, an active area of research where the resistance actually goes all the way to zero. Not just close to zero, actually zero. And I'll do a video and demonstrate that for you. It's a totally different animal. It's not an everyday situation, and you have to cool them down with liquid nitrogen. All right, next I want to talk briefly about AC versus DC. I'm going to do a separate video on that also, but I want to reiterate and tell you that this power supply provides DC. When I dial it up here, it's a constant voltage. It never changes in a certain direction. This positive terminal is the higher voltage. That's why it's positive compared to the black terminal, which is at a lower potential. So the black is a higher voltage relative to the red is a higher voltage relative to the black wire, right? I told you voltage is always between 2 points, right? But in a battery, you have the same situation. You have two sides of a battery. It's a direct constant voltage leading to a direct current that goes in one direction. Solar panel is the same way. And so most things that we do in hobby circuits are usually direct current, right? Phones, things like that, when you're using them, direct current. But everything that's generated by a power plant and sent to your house is what we call AC, alternating current. And that means that instead of the voltage being constant, the voltage actually goes up, and then it goes down back to zero, and then it swings the other direction, and it starts to go negative voltage and then back up in a kind of a sinusoidal pattern. And we can actually see this here, over here. So I have this function generator up set to a sine wave here. I do want to change the offset here a little bit. I want to change, let's see, I want to change the high level, and low level. Yeah, I want to change it to -3, I think. So -3. And I want to hit volts. So what's going to happen is this thing's going to jump down so that it's a sine wave that looks like something like what would come out of your wall socket. Now, it's not really at all the same because the voltage is different, but the shape of it is the same. That's what I mean when I say that it looks like what would come out of your wall. What's happening here is that basically inside of this conductor, there are actually two wires, right? You can see the two wires are connected over here. And what it means is that when I'm going up on the positive side, then the red wire, the red wire here is going higher and higher and higher in voltage. That means the current is coming into the circuit through the red wire and going through there. But eventually, the voltage drops back down to 0. Remember, this tick here is the 0 axis here, so it goes back down to 0 volts, but then it switches to negative voltage. Negative just means that it's as if I flip the direction of the wires. So instead of the current coming out of here, what actually happens is the current starts to go back through the wire and starts to come out of the black wire. So it's almost like if you could grab them, it would be like current going this way, but then switching around and then going the other way, and then going the other way, and then going the other way. So the voltage is going positive and then negative, switching polarity back and forth, and that's driving the current in, but then it turns around and it comes back out. So it's going, if you have two little prongs in your outlet in the wall, it's like current's going kind of like out of one and into the other, but then it turns around and it goes the other way. So literally it's alternating back and forth, back and forth, back and forth. In the United States, 60 times a second, 60 hertz. In other countries, it's a different frequency. Now you might say, why do they make it like that? Why does it have to alternate? Well, it's because of the way it's generated. And I'll have a whole video on it, but because it's all generated with rotating motor generators, steam is flowing through a turbine and it's turning a generator, and the magnetic field is rotating in a circle, then half of the circle it's generating positive voltage and the other half of the circle is generating negative voltage. As it turns around, it traces out this sine wave. So this shape, this sign that we learn about in school is so important because when we use circular generators to generate a voltage and it's rotating, if you remember, the sine function comes from a circle, projections on a circle. That's why the shape of the voltage is a sine in the first place. All right, now the last thing I think I want to say before I close it out is just one more word on units. So I want to talk about units because we're going to use units a lot as we build things. For current, we use amps, which we abbreviate A. But I just want you to know that the metric system applies to this. We might talk about milliamps, right? We might talk about milliamps, 1/1000th of an amp, just like a millimeter, right? And then we might have microamps, which is 1/1,000,000th of an amp, right? Now you can have kiloamps and things, but usually you're not doing that unless you're building nuclear power plants. So usually you're talking about milliamps almost all the time, or sometimes amps, right? Now for voltage, which is the push, the voltage we talk about in terms of usually millivolts, so MV, millivolts, but because we have, it's fairly common when you deal with not necessarily power plants, but we also run into kilovolts sometimes, so we'll put kilovolts there. And you might have megavolts, right? If you're at a nuclear power plant or something like this. But usually in a circuit, it's millivolts or volts, and milliamps or amps, maybe even microamps. And then we have resistance. This tells us how much the current is being impeded. The unit of that is called an ohm. Oftentimes we're talking about milliohms, so it's a little m with an ohm. And that's 1/1000th of an ohm. Or micro ohm, which is 1/1,000,000th of an ohm. Oftentimes in resistors we talk about kilo ohms, and we also talk often about mega ohms. So thousands of ohms, millions of ohms. Most of the resistors you're going to use, like in the circuits that we did here, they're just going to be the base unit of ohms or somewhere in the kilo ohm range, right? Most of the voltages you're going to use in a circuit are going to be in the volts, 1 or 2 volts, maybe in the millivolt range. Most of the current you're going to be dealing with are going to be in fractions of an amp or in the milliamp range. Anything outside of that, usually you're dealing with very specialized or more advanced situations. So that's it. That is what what I wanted to present to you. I wanted you to understand voltage and current and resistance with practical circuits, understanding how resistance impedes the current flow and lowers the current value, which we did with the light bulb. And hopefully now you have an intuitive understanding of how they fit. As we go into future lessons, we'll use Ohm's law to calculate the current or the voltage, and we'll be able to calculate numerically what a circuit should be able to do. Learn anything at mathandscience.com.